Okay, so the red area would be the area bounded between a and b of g of x dx. Whoop. The green area is the area from a to b bounded between f of x and the x-axis. We write it like that. So what would I do in order to get the blue area? Yes, I would subtract the two areas, g of x from f of x. And so, if you wanted to find the blue area, you would take the integral a to b f of x dx minus the integral from a to b of g of x dx, which is the same thing as the integral from a to b of f of x minus g of x dx. I'm very proud of you. It is an integral symbol. Very good. Okay, so find the area bounded between y equals x squared and y equals negative x plus 6. We're going to go with plus 6. I think I messed this up. So we did it. Over the interval 0 to 2. So this sounds like a difficult topic. We are going to find these areas. We'll eventually revolve these around the x-axis and the y-axis. They'll create different shapes. I would be lying to say that people find this unit easier than the last one. I'd be lying to say that they did find it easier than last unit. I would say, yeah, I would say most people find this more challenging than last unit, and it all has to do with this, their spatial reasoning. Some of you are gifted with the ability to understand spatial reasoning, and some of you will struggle with it more. It is crucial in this topic that you would be able to sketch the graph, okay? So we start by sketching the graph. What does x squared look like? It's like a parabola. Yep, centered at 0, 0. And what does negative x plus 6 look like? I really need to verify where those intersection points are. I really do. Because it's so important that in our expression for formula bounded between two curves that we identify the top function and minus the bottom function. And as you can see here, if I put my black marker right here, what's the top function there? The line or the parabola? The line. If I put my black marker there, what's the top function? Parabola. So depending on where you are, the top function, bottom function can change. So it says over the region from 0 to 2. I know 0 is here, but is 2 right there? Is it back? Is it over? Where is it? So we should find where they intersect. And where we find where they intersect by taking the two functions and setting them equal to each other. So where is x squared equal to negative x plus 6? X squared plus x minus 6 is equal to 0. That factors to what? So I have a positive 2 and negative 3. So it looks like This intersection point right here occurs at -3, and this intersection point right here occurs at +2. So what we're looking for is the area bounded between the two curves from 0 to 2. So that's the section. What is the top function for the area? -x plus 6. What's the bottom function? X squared. So as I set up my integral, I have the integral bounded from 0 to 2 of the top function, -x plus 6, minus the bottom function, x squared. Scott, I don't know if I got your question. Yes, so right here, the line is on top. Right here, the parabola is on top. Since I'm looking at this black area right here, I identify that the line is going to be the top function. Okay. Yes. But it's should highlight something. Sorry. So you'll want to ask questions like, will it always be this way, always be this way? These are basic problems today. We'll get to much more difficult problems. Okay, so this is the foundation. Things will change. We will, instead of doing top to bottom, we will do right to left tomorrow. Okay, and it will change things. So. All right. Okay, so here we go. I have the integral. So on the test, I will do a few things. Number one, I'll make sure that you can draw the function accurately, that you can represent the shaded region appropriately, that you can set up the appropriate integral. The last part is review for us, isn't it? Actually, evaluating this is not that big of a deal. So I would say that the most difficult part for people is setting up the graph and the integral. So let's evaluate it now. From 0 to 2, negative, whoop. I have a -x squared minus x plus 6. Let's take the antiderivative. Hold on, folks. Let me just check. Yeah, let me check. So, B lunch, we get out at... Just go. We'll pick up when we get back. Okay, here we go. What grade is your sister in? Oh. New since start school. Very good. Okay. So we got -x to the third over 3 minus what? Very good. X squared over 2. Evaluated from 0 to 2. So it's nice when we get to plug in 0 because, you know, it all goes away. We just plug in 2 and we get -8/3 minus 2 plus 12, right? And when we evaluate that, -8 over 3, 10/3 would be 30/3. The area between two curves will always be positive so long as you do the top minus the bottom, always. If you do the bottom minus the top, it will be negative. Okay, so you should always do top minus bottom. If you come up with a negative, you either put the wrong function on top or you did something else wrong. Is that clear? So we finish that problem off. Let's flip on over to the next side. Okay. Find the area bounded between the curves y equals x squared minus 2x plus 1 and y equals 2x plus 1. How is this different from the previous one? Okay. Different numbers and stuff. Yep. There's no bounds that are specified here, so we would have to actually find the intersection points then. X squared minus 2x plus 1. This does factor to x minus 1 times x minus 1, right? So that means it has a double root at 1. So as you want to come up with the graph, remember if you're doing a parabola, negative b divided by 2a, or in this case, the x-intercepts were easy to find. So I know it has a y-intercept of positive 1. I know it has an x-intercept of positive 1, double root, so it's just going to touch and bounce off. And 2x plus 1 is a line that has a slope of 2 that's going to pass through 1. So something like that. And it's very important that as we draw this each time, remember the way that we find areas, we add up an infinite number of rectangles. So the idea is you're going to draw a rectangle from the top to the bottom. It's important you understand that idea that we're really drawing from the top to the bottom here. Okay? So, because that changes as we go along. So you can see the area there. So, what is my top function? Y equals 2x plus 1. And the bottom would be y equals x squared minus 2x plus 1. So we have our top and our bottom. We should find our bounds. So we will have one bound right there and another bound right at 0 is plain to see. If we set the functions equal to each other, how do we solve? You can see that the 1's cancel. You get x squared minus 4x equal to 0. Take out an x. So it confirms that you have a 0 at 0, and then you also have 1 at 4. Now you can set up the bounds appropriately. Or I'm sorry, set up the integral appropriately. Our integral goes from 0 to 4. We have the top function, 2x plus 1, minus the bottom function, x squared minus 2x plus 1, dx. Do you notice? The 1's cancel. Looks like we have a negative x squared. 2x minus a negative 2x. How's it 4x? Dx. Okay. What's the antiderivative of negative x squared? Plus the antiderivative of 4x, 2x. Four to the third. Negative 64 thirds. 4 squared is 16 times 2 is 32. Thirty-two can be written as 96 thirds. Thirty-two thirds. Not too bad. Yeah. Definitely after spring break. We will not test this week. We've got a lot of material to get through. We will be doing. So right now we are integrating. We're drawing from top to bottom, which means we're stacking the rectangles left to right. We will also do it where we stack the rectangles on top of each other. We'll also take the shapes and revolve them around. So we're going to do a lot of different things. Definitely after break. But as you look at the problem, again, if you were asked to find the exact area bounded between two curves, without the integral, that would be very difficult. But the integral and calculus make it quite simple as long as we can draw it out. Okay, let's look at a trig example. Find the area bounded between the curves y equals sine of x and y equals cosine of x over the interval 0 to pi over 4. 0 to pi over 4. So first of all, do you remember what the graphs of sine of x and cosine of x even look like? What's the period? Period is not 1. Period is 2 pi. Amplitude. So I'll grab sine of x in red. Sine starts at 0 or the max or the min. It's going to start at 0. And I'll do cosine in green. Cosine starts at 1 and then it goes down right away. Remember those good old days? And we're looking at the integral from 0 to pi over 4. So I should make sure that the area is for sure this section right here. It would seem reasonable the way the problem is set up that we'd be just looking at that. But we should be very careful. You know why? Because if this, let's suppose that we would go a little bit further. Let's say pi over 4 wasn't to there. Then the top and bottom would switch, wouldn't they? So we'd have to set up two different integrals after the switch. So let's verify that that is for sure pi over 4. We hope it is. So we take sine of x and set it equal to cosine of x. Anybody remember from your trig last year how we solve an equation like that? Good. Sine squared plus cosine squared is 1. We could use that. It would take a long time. So we get tangent of x is equal to 1. Where is tangent equal to 1? Inverse, you get pi over 4. So that is the solution right there. Yep, one of the solutions, because you can see you have another one right here. That'll be at 5 pi over 4. So we're just looking at that spot. So fortunately for us, it's right there. So that interesting shape, it has an exact area that we could calculate. So I set up my integral. The integral from 0 to pi over 4 of, what's the top function? Cosine of x minus, what's the bottom function? Sine of x dx. The tricky part about this problem for a lot of people is taking care of your positives and negatives appropriately. Antiderivative cosine. Positive sine. Antiderivative of negative sine. Positive cosine. Evaluated. In this case, the 0 doesn't just go away because cosine of 0 is 1. So we start with pi over 4, sine of pi over 4. Root of 2 over 2. Remember, pi over 4 is how many degrees, you guys? 45. So you have a 45, 45, 90 triangle with a hypotenuse of 1 in the unit circle. You divide it by the root of 2 to get the other side, which is root of 2 over 2. And that's going to be the same because it's a 45, 45, 90. So that is your coordinate, root of 2 over 2, root of 2 over 2. And as sine the x value or the y value? Sine is the y value. So we have root of 2 over 2 plus is cosine the x value or the y value. The x value, root of 2 over 2 minus, plug in 0 and you get 0 plus 1. What is the root of 2 over 2 plus the root of 2 over 2? Just the root of 2. That's the That's the exact value. All right. So, good work. That's the basic area between two curves. We could try much more difficult ones later. I know that Cassie's hoping for something more challenging. You can see she's getting bored with this lesson. It's pretty easy. Question. Fourth hour is so fourth hour goes 48, 50 minutes because you need to get lunch in. After this, you're back to 33-minute classes. There's your assignment.